Dear students, Jai Hind. Myself Dr. Panka, Assistant Professor in Electronics and Communication Engineering Department at AKGEC. Today's topic of discussion is delta modulation and adaptive delta modulation techniques. Delta modulation and adaptive delta modulation are digital modulation techniques which are used to transmit the message signal using 1-0 logic 1 logic 0 form. Delta modulation is obtained by simplifying the quantization and encoding process of PCM. Now what happens in case of pulse code modulation? We assign a number of binary bits to each quantization level, and corresponding to each quantization level we transmit these bits. Say for example, if we have 8 quantization levels, then to represent these 8 quantization levels using binary, we need 3 bits. Okay, so say we have 8 quantization levels, then for 8 quantization levels we have say 0, 1, 2, 3, 4, 5, 6, 7, 0 to 7. There are 8 quantization levels. Then to transmit these quantization levels using digital techniques, we need to convert these quantization levels in binary form. So we assign binary values to these quantization levels. So we can see here each quantization level is represented by 3 bits, 3 binary values. First quantization level, which is denoted by 0, is represented by 0, 0, 0. Similarly, the last quantization level is represented by 1, 1, 1, and so on. So for each quantization level we transmit 3 bits, that is PCM. Now delta modulation is a simplified version of data transmission. Here we used to save the bandwidth, and we will see how we can save the bandwidth by using delta modulation technique. First of all, in case of delta modulation, for each quantization level we don't need to transmit all 3 bits as in case of PCM. We can transmit lesser number of bits for each quantization level in case of delta modulation. How? Let us see. Now in case of delta modulation, one thing is that we take a higher sampling rate. The benefit of taking higher sampling rate is that the gap between successive samples will be less, and if the gap between successive samples is less, it means they are more correlated to each other. The correlation between the samples will be higher. It leads to higher correlation among the successive samples if the sampling rate is high. Now under this condition, it may be safe to assume that any 2 successive samples are different by an amplitude of delta. That is, the current sample is either larger or smaller than the previous value by delta. Okay. Now if we have to transmit this information, then we can see if the next sample is greater than the previous sample by a value delta, then it may be considered as positive, and if the next sample is smaller than the current sample, then it may be represented as 0. For plus delta, we say it is plus, it is denoted by logic 1, and for minus delta, it is, we say, logic 0 and denoted by 0. The quantization and encoding blocks in this case becomes very simple. Thus, if we have the first sign value and 1 bit quantization information, we can reconstruct the complete quantized signal. Let us see this waveform. Here in this waveform, we have this message signal xt. Now, if we have to represent this message signal using quantization and binary information, then here we can see that during the initial phase, when our message signal is rising, we can say that the next sample is greater than the previous sample. Each next sample is greater than the previous sample, because our sine wave, this is increasing, is in increasing order. So next sample will always be greater than the current sample. So here, because the difference is plus delta, as we can see here, the difference is plus delta because the next sample is greater than the previous value by an amount delta. So it is denoted by logic 1 up to this point, and our staircase waveform, which is the quantized waveform, is trying to catch up with the message signal. Now, during the time when our message signal is decreasing in amplitude, we can safely say that the next sample, each next sample will be smaller than the previous value by an amount minus delta. So we can denote this minus delta by 0, and our staircase waveform, we can see here that it is trying to catch up with this message signal. So xt is our input message signal, and this ut here is our quantized waveform, quantized wave, and corresponding to this quantized wave, this is our generated binary data. So instead of sending multiple bits for each quantization level, as we do it in case of PCM, here in delta modulation, we take the difference between the successive samples, and if the next sample is greater than the previous one, then we send 1, and if the next sample is smaller than the previous sample, then we send 0. So only 1 bit is transmitted. For each sample, only 1 bit is transmitted. That is the benefit of delta modulation, that the number of binary bits which are required to be transmitted is less. So the bandwidth consumption is smaller. So we save our bandwidth, and also the power saving, power consumption is saved. Now, this delta modulation technique, which we just discussed, has two drawbacks. There are two kinds of noises that occur here. One, when the slope of the message signal is very high, and the second, when the slope is 0. Now, first case, when the slope is very high and our step size that we have chosen is not sufficient enough to catch up with the message signal, then there is a gap between the message signal and the quantized waveform. This gap is denoted here, this part, this gap. This is the noise. This is the gap between message signal and the quantized waveform, and this is actually the noise, quantized noise we can say, and it should be minimum. If it is more, then our output will not be matching the input. So it is a distortion. Now, the second type of noise that occur in delta modulation is known as granular noise. Here we can see our input signal is constant, it is not changing, but our output is changing, whereas our output can be constant in this case because input is constant, but still our output is continuously changing. This is the granular noise. Now, these two type of noises that occur in delta modulation, they can be minimized to a great extent if we use the adaptive delta modulation technique. Okay. In adaptive delta modulation technique, what we do is we make the step size variable. In case of delta modulation, step size was constant. So, in case of slope overload error, our step size was not large enough to catch up with the slope of the message signal. Similarly, in case of granular noise, because the input is constant, if our step size is smaller, then we are closer to the message signal. So, if we can vary the step size as per our need, then the slope overload error and the granular noise error can be minimized to a great extent. So, that is the feature of adaptive delta modulation, where step size is variable. Now, let us discuss the block diagram of delta modulation and adaptive delta modulation. Please see here. This is the block diagram of delta modulation technique. Here you can see that we have a comparator circuit here. This is our comparator. In this comparator circuit, we are comparing the incoming message signal with the output of this delay section. This is denoted by X cap, and the incoming signal is X. Now, what we are doing here is the message signal is compared with the delayed version. That is, this is actually the previous sample. Okay, this is the previous sample which is compared with the next sample, and their difference is taken as the error. Okay, we are comparing the two successive samples, the previous sample and the next sample, and their difference is denoted here by error, which is quantized, and this error signal or this quantized version, it may be plus delta or minus delta. If it is plus delta, then we transmit 1. If it is minus delta, then we transmit 0. There are only two levels in delta modulation, 1 and 0. Okay. So, the next sample is compared with the previous sample. The error is taken here, which is quantized, 1-bit quantizer is used, and the output of the quantizer is denoted by EQ. Okay. Now, if this quantized value is positive, then 1-bit logic 1 is transmitted. If this quantized value is negative, then logic 0 is transmitted. Here, this is a delay element. The quantized value and the previous value of delay module is added. Okay, and the previous value of this delay module plus the quantized value is added here, which is again fed into the delay section, and the next value at the output of delay will be compared here with the next sample value. This is the delta modulation. Okay. So again, simply we can see that the next sample is compared with the previous sample. The difference is taken as E, which is quantized and denoted by EQ. If EQ is positive, then logic 1 is transmitted. If EQ is negative, logic 0 is transmitted. This delay section only what it delays the sample by 1 position. Okay. This is the delta demodulation. Here we have taken this summing circuit which add the one bit information which is coming from the transmitter section. This is a 1 bit information. This is coming and this is adding to the delay value to get the message signal. This we can see. When this message signal, reconstructed signal is passed through the low pass filter, then we get the proper demodulated output. Now, let us see the block diagram of adaptive delta modulation. See, in case of adaptive delta modulation, there is an additional logic which is used to control the step size. In case of delta modulation, we had this section only. Delta modulation. Now in adaptive delta modulation, we have added another intelligence, another level, that is the logic for step size control. So our step size is not fixed to delta, it may change as per our requirement. We can see this with the help of a waveform. We can see here we can see as the slope of the message signal is very high and our existing step size, say this is our existing step size initially, it is not able to catch up with this slope. Then what we did, we started increasing our step size. We can see here in this waveform, the step size is increasing, and the benefit of increasing the step size is that the gap between the message signal and the quantized waveform is reduced. The gap, this is the gap. This is the gap. This gap is reduced. So the slope overload error is minimized by increasing the step size. Similarly, in case of granular noise, we can see the gap is reduced by decreasing the step size. Here we can see the step size is decreased. Step size is decreased. So this is our gap between the message signal and the quantized waveform. This gap is narrower as compared to in the delta modulation technique. Here the gap is more. We can see the gap is more. In case of adaptive delta modulation, the gap is lesser, and it is because we can reduce the step size as per our need. So Here, in case of slope overload error, by increasing the step size, and in case of granular noise error, by reducing the step size, the gap is reduced and so the error is reduced. For this topic, the reference books we have taken is the book Simon Hickin, Communication System from John Willey and Sons. Second book that we have referred is Taub Schilling, and the title is Principle of Communication System, Tata McGraw-Hill. And the third one is George Kennedy, Electronic Communication System, McGraw-Hill Education, 6th edition. Thank you.